Hi, I'm Saurabh, and this is KKNet-Terahertz, an AI-powered real-time channel estimation engine for 6G terahertz wireless communications. Here's the problem. The next generation of wireless, 6G, will use terahertz frequencies between 500 GHz and 1 terahertz. This unlocks insane bandwidth. We're talking 100 plus gigabits per second, enough to power autonomous vehicle networks, holographic video calls, and smart city IoT meshes. But there's a massive physical barrier. At these frequencies, the wireless signal gets destroyed by three things. First, water vapor in the air literally absorbs the signal at specific frequencies, 560, 752, and 988 GHz. Second, the signal bounces off walls, floors, and ceilings, creating messy multipath reflections. And third, the signal weakens dramatically over even short distances. To communicate reliably, we need to estimate exactly how the wireless channel distorts the signal, and we need to do it in under 2 milliseconds. Traditional physics-based methods take seconds. That's way too slow for real-time 6G. So we built a deep learning model that does it instantly. First, let me show you the foundation, our physics simulation engine. We built a complete terahertz propagation simulator from scratch in PyTorch. It models free space path loss, molecular absorption, 10 non-line-of-sight reflection paths, and a local oscillator mixing stage. This simulator generates two things: the time domain intensity waveform, which is what a real receiver would physically measure, and the ground truth channel transfer function in the frequency domain, which is what we need to recover. We generated 16,000 samples, and the entire simulation runs on the GPU. Now, the AI. This is KKNet. It's a custom 1D convolutional neural network. The architecture has a feature extractor that acts as a learned matched filter, and a regressor that maps those extracted features directly to 800 output values of the complex channel response. The key innovation here is that a standard photodetector only measures signal intensity. It completely loses the phase information. Our model performs automatic phase retrieval. It recovers both magnitude and phase from intensity-only measurements. We trained this with strictly no data leakage. The result? A normalized mean square error of approximately -34 decibels. Now let me show you the interactive demo. The physics simulator and the AI model are running live on my GPU right now. On the left, you see the raw time domain intensity waveform. On the right, the blue curve is the ground truth channel response, and the red dashed curve is what our AI predicted. Notice how they overlap almost perfectly. Now watch what happens when I increase the humidity. See those deep V-shaped notches appearing at 560, 752, and 988 GHz. That's water vapor molecules resonating and absorbing the signal. This is real physics. And look, the AI's red prediction curve follows every single one of those sharp dips perfectly. Now I'm increasing the communication distance to 25 meters. Watch the magnitude drop across the entire band. The AI tracks this degradation accurately. This is the power of deep learning applied to physical layer signal processing. So what's the real-world impact? For 6G smart cities, autonomous vehicles need sub-millisecond channel updates. Our model runs inference in under 2 milliseconds. For green computing, replacing heavy physics computations with a lightweight neural network reduces the computational energy footprint at base stations by over 99%. And for atmospheric sensing, this same model can detect greenhouse gases and pollutants using terahertz spectroscopy. To summarize, we built a complete end-to-end system, from a GPU-accelerated physics simulator grounded in electromagnetic wave theory to a custom deep learning architecture that performs real-time phase retrieval. This is not an API wrapper. This is custom scientific machine learning solving a real, unsolved infrastructure problem for the next generation of wireless communications. Thank you.